Okay, let's start off by going through this assignment. So they name the type of energy present in fossil fuels. So that is chemical potential. Identify the type of chemical reaction used to release energy stored in fossil fuels. This is combustion. Write a formula used to calculate energy change for combustion reaction using the standard heats of formation, and identify each variable in the formula. I'm still in the library, so I can't write this down, but it's that delta RH equals sigma n delta formation of products minus reactants. Just do products minus reactants and multiply it by the moles and you'll be good. Define heat of combustion. So this is heat given off in combustion reaction where a hydrocarbon reacts with oxygen, makes CO2 and H2O. Standard heats of formation is the heat given off or absorbed in a formation reaction when it's formed from elements. Describe the result of a change in potential energy during a chemical reaction. So the result of a change in potential energy can give off energy if it's combustion, or it can absorb if it's endothermic, but most of the time it's going to give off energy. And draw an energy diagram for an exothermic process indicating the position of the reactants and the products. How will I do this? Insert. Can I insert a drawing? Well, let me just do it on this. So this is a potential energy diagram for combustion. This is delta H, and you have your reactants and your products over here. And this is potential energy. And then this is, usually we say reaction progress. It's not really time, but as the reaction progresses, that's what it would be. Okay. And then these ones, the answers are all given. So if you couldn't get those answers, shoot me an email and I can help you out with getting those answers. Or if you send me an email with your work, I can pretty easily tell you what you're doing wrong if you show me that work with everything in there, just like I showed you in the lesson. Okay, so let's do this. So let's do the sample diploma questions. So the equation that can be used to determine the quantity of energy released from combustion. So it's combustion, it's going to be D. So this is the heat of our reaction. This is sum of those coefficients. And then the products, the heat of formation of products, sum of coefficient times the heat of formation for the reactants. Okay. And then this question here, we're burning methane and we want to find the combustion of methane. So let's do that question. I'm just going to write it down. Okay, let's switch the screens here. Okay, so CO2, so we'll go 1 times, and then CO2 is negative 393.5 kilojoules. Because there's a 1 in front, there's a 2 in front of this. So 2 times negative 241.8 kilojoules. Let me just double check those because I'm going off of memory here. 393.5, 241.8, perfect. And then we're going to subtract our reactants. So there's 1 of the methane. So methane is negative 74.6 kilojoules. And of course we leave off the oxygen because elements have an energy of 0. And we'll type this all in. Remember, you need double brackets around your reactant when typing it in. You need those double brackets in your calculator. So we'll go 1 times negative 393.5, and then 2 times negative 241.8. Close those brackets, and then we'll subtract it from 1 times negative 74.6. And you should get 802.5 as your answer, which is C. Okay, so this is our lesson on nuclear energy. We're going to break it into 2 parts. So this is the first part, and then I'll do the next part, the next lesson. So lots of curriculum stuff here. Explain the difference between fission and fusion, and balance the simple nuclear equation to show conservation of nucleons. Describe the main sources of radioactive decay. So you need to know about alpha, beta, and gamma. Describe mass energy changes in fissions and fusions. So we have to use the formula E equals mc squared. Make sure you know the difference between fission and fusion. Describe in general terms the operation of a fission reactor. So you have to know how a nuclear reactor works generally. Compare and contrast coal, oil-fired, or hydroelectric stations with nuclear. So you need to know those energy conversions, like I was talking about. Those are important in design and function. Contrast quantitatively the orders of magnitudes of energy produced in a nuclear, chemical, and phase change, and then calculate mass energy, again using E equals mc squared, and that's it. So what's inside the nucleus of an atom? Okay, so this here is the nucleus. And in the nucleus you have these positive things, which are protons. And then you have the non-positive things, which are neutrons. And then these guys outside of the nucleus are our electrons. Okay, so in your periodic table, you'll find a lot of information about what's in the nucleus. Let me just open the periodic table here. Just 1 second, opening it up. Site 30, data booklet, there we go. Here we go. So this tells you a lot of information. So the first thing I want you to notice is this number right here. This number right here. So that indicates the number of protons. So if we look here, we have 1, 2, 3, 4. So we have 4 protons, which would tell us that. So that 4 protons is important because it tells us what the element is. So if we look at what element has 4 protons, well, the one with 4 is beryllium right here. So we can also add the symbol Be to this. Okay. So the mass of beryllium, the mass of an atom, so this is a beryllium atom, comes from the nucleus. So all you have to do to find the mass of beryllium is you just have to count up how many, they're called nucleons. So neutrons and protons are found in the nucleus, so they're both nucleons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this beryllium would have a mass of 9. Because it's got 9 things in the nucleus. That's it. But when we look at our periodic table, you'll notice that it says the mass of beryllium is 9.01. And that's because there's different isotopes. So I think I'm jumping the gun with talking about this. I'm actually going to save this. So I'm just going to put the mass number down here. So that's the mass of it, and that's all you really need to know from the periodic table. Another thing that you should know as well is that if there's 4 protons, so there's 4 positive charges, there has to be the same number of electrons. So let's jump in the gun with isotopes. So isotopes are the same element but different masses. So what makes up the mass of the element? Well, nucleons, the things inside of the nucleus. So those are protons and neutrons, right? This here inside the nucleus makes up the mass. Electrons are crazy light, so they don't affect the mass. So if you just have to count up how many protons and neutrons, and then that's the mass. So what happens if I change the number of protons? So let's say we took our beryllium atom and we added another proton. Well, if we added another proton, oops, what's going to happen is, well, it's not going to be beryllium anymore. What it's going to be is it's going to have 5 protons, so it's going to change into boron. If we add another one, it would change into carbon. So if we change the number of protons, we change the element. What happens if I change the number of neutrons? Well, the number of neutrons don't make up the element, but the number of neutrons make up the mass. So what we would change is we would change the mass. Okay. So what an isotope is it's the same element but with a different number of neutrons. Okay, so I'm going to go back to what I was talking about before. So this, ignore this extra proton, this is beryllium-9. It is a mass of 9. I could also add on another neutron, and if I added on a neutron, it would have a mass of 10. If I added on another neutron, it would have a mass of 11, but it wouldn't change what it is as long as I'm only adding on neutrons. So this mass of 9.01, this is an average. So if I have a bunch of things, a bunch of balls here, a bunch of nuclei, nucleuses, and a bunch of them have a mass of 9. Okay, most of them have a mass of 9. And then one of them has a mass of 10, right? What this number is it's an average. So if I take my calculator and I go 9 plus 9 plus 9 plus 9 plus 9 plus 9 plus 9. So that's how many 9s I have. And then I have a 110. And I find the average, so I divide it by how many there are. 1, 2, 3, 4, 5, 6, 7, 8. So I divide that by 8. You can see I get this 9.125. So this is an average. And what's important to know is that this number is an average down here. So these are all my different nuclei. Do any of them have a mass of 9.125? No. They have a mass of 9 or they have a mass of 10. But because we're averaging them, we get this fractional number, and that's what's happening here. So what this tells us is that most of them are 9, and there might be a few 10s in there as well. Okay? This is not the mass number, it's just an average. None of them have that number, so it's important that you know that when doing questions. Okay. So nuclear notation. So the chemical symbol for any isotope is designated by stating the atomic number in subscript, the mass number in superscript, and then the element symbol, which we call X. So this is nuclear notation. So what that means is it's super confusing, but it's not that confusing, is if we took beryllium, so we take our symbol, so this A represents our mass number. So we said it had a mass of 9, so we put the 9 up top. And this bottom number represents the number of protons, and we said that had 4 protons. So bottom number is protons, top number is mass number. And the way that I remember that the top number is the mass number is it's kind of set up like elementary subtraction. If we ever wanted to find the neutrons, all we would have to do is go 9 minus 4, and we'd find that it had 9 neutrons. Okay. So let's do a question. So we're going to put it, I should say nuclear notation. So nuclear notation, we're going to fill out all of these. Okay, so potassium, I can find the symbol for potassium. So potassium is right here. It has the symbol K. Okay. So I'm going to fill in the symbol K. So I know that. So they tell me how many neutrons I have. And for it to be potassium, well, it has to have 19 protons. So I also know 19 protons. So protons and atomic number are the same thing. And then it's always going to have the same number of protons as electrons, so we can fill that all in. To find the mass number, what a lot of people do is they're like, oh, the mass number is 39.1. No, that's an average. We want to find out the specific isotope of potassium, what its mass is. So all we have to do is add those two numbers together to find our mass number, which will give us 40. So calling this potassium isn't good enough. We need to call this potassium 40. And now we're ready to fill in our whole nuclear notation. So the top number is our mass number, and the bottom number is our number of protons, and we're all filled out. Okay, try this board question. Pause the video, do it, and watch to see if you get the right answer. Okay, so the element B is boron. And it's not okay to just say boron, because if we look at the periodic table and we look at boron, this is the average mass. So some of them are probably 11, some of them are probably 10. We want to know which boron it is. So this tells us that this is boron 11 because it's got a mass of 11. So we know that we have 11 as a mass. The bottom is our atomic number, which is our number of protons, and we always have the same number of electrons. And then to find neutrons, it's set up like subtraction. 11 minus 5 is 6. So we must have 6 of those as neutrons. Right? And if we go 5 plus 6, we get 11. That's the right answer. Okay. Try this one, pause the video again, see if you can get it. Okay. Number of protons is atomic number. It's the same as number of electrons. So we have to look up what element is number 47. So 47, here is silver. So silver, and silver has a symbol Ag. So to find the mass, I need to add these two together. So I get 107. So this is specifically silver 107, and it's got a mass of 107, and it's got 47 protons. Okay, you got to know how to do that. So the strong nuclear force is what holds the nucleus together. The strong nuclear force is stronger than gravity, stronger than electric, stronger than magnetic forces. And when the nucleus is too unstable, it's going to break apart in a process called radioactive decay, right? So you have, for example, the helium nucleus is pretty stable, but if we add on too many neutrons, what's going to happen is it's going to become unstable, and this strong nuclear force that bounds us together is not going to be weak enough, and it's going to break apart into other things. Okay, so after it breaks apart, the nucleus always becomes more stable. That's why it does it. So during one way that it can break apart to become more stable is by emitting an alpha particle. So an alpha particle is 2 neutrons and 2 protons stuck together. It's the same as a helium nucleus without electrons, and it can be represented in 2 ways. So one way to represent an alpha particle is with a little fish symbol here, and it's got a mass of 4, and it's got 2 protons. Or the other way of representing it is it's the same as helium, right? 4 and 2 is going to be helium. So what an alpha particle looks like, I kind of drew it last time, is it's got 2 protons, 2 neutrons, so it's got a mass of 4, and then 2 protons. So you don't have to memorize that. You can find that in your data booklet here. So here's an alpha particle, and it gives you information at the top there. So it gives you information about the alpha particle. So that's on page 8 of your data booklet. So let's do an example. Many smoke detectors contain the isotope americium. Kind of looks like mercum, but it's americium. Alpha particles emitted during the decay of americium will ionize and allow an electric current to flow between 2 plates in a smoke detector. During a fire, smoke particles come between the 2 plates and interfere, cutting off the detector's alarm. Write this alpha decay. Okay, so lots of extra information here. Americium 241. We can look that up on our data booklet. So here's americium 241. So americium has to have 95 protons, and it's got a mass of 241. So we have Am 241, and it's got to have 95 protons. So what that americium does is it emits an alpha particle. Okay, so you can write it any way that you want. I'll write it like this for this example. So it emits that alpha particle. What it's going to turn into is something that's more stable, and it has to have the same number of these nucleons, these masses up top, and it's got to have the same number of protons. So if I have 95 and then I lost 2, what I'm going to be left with is 93. If I have 241 and I lost 4, well, that's going to be 237, right? 237 plus 4 is 241, 93 plus 2 is 95. Both sides should always add up to the same thing. So we have to look up, well, what is this element number 93? So element number 93 is here, which is neptunium. So it's going to turn into neptunium. Okay, give this one a go. Same thing. Okay, so you have to look up thorium-230. Here, thorium, which is number 90. Thorium-90, 230, like that. It emits an alpha particle. And if it emits that alpha particle, well, if I have 90 and I lose 2, I'm going to be left with 88 on the bottom, and 230 minus 4 is 226. So I'd have to look at what's going to be 88. Yeah, 88 is right here, which is radium, so Ra. That's what I'm left with. Okay, easy peasy. So another type of decay that a nucleus can do is beta decay. So it emits beta radiation, and beta radiation is just an electron. So again, we can express it in two ways. So one is using the Greek symbol, which is like a B with a longer tail. And I talked about how electrons are so light, they don't factor into the mass. So it's got a mass of 0, and it's got a charge of -1. The other way that we can write it is just as an electron, like that, so an E, and then 0 and -1 as well. Both are acceptable. Okay, so carbon-14 undergoes beta decay right out the reaction. So carbon-14, and then you got to look up how many protons are in carbon. So carbon's right here, which is number 6. So that's what it's going to be. So it emits a beta particle. And this one's a little bit trickier. Well, the top is easy. 14 plus 0 is 14, so that's good. But this is -1. So I have to find a number here that if I add it to -1, it's going to equal 6. So that's going to be 7 plus -1 is going to be 6. So this number ends up getting bigger. And if we look up what 7 is nitrogen. So carbon turned into nitrogen. Okay, try it on your own. So krypton 87. So we got to look up krypton, which is here, number 36. It emits an electron or a beta particle. So this number is going to get bigger on the bottom. It's going to become 37, but the top number stays the same. And we have to look at, well, what is 37? 37 is here, rubidium. So it's going to turn into rubidium. That's it. Okay, so alpha and beta emit alpha particles, beta particles, so it emits a stream of particles. Gamma radiation is an electromagnetic wave. So because of this, it has no mass and no charge, and it can be expressed like this. So gamma, in your data booklet, is like this. And it has no mass, it has no charge, and it's only expressed in one way. And again, all this information can be found in your data booklet. Like this. It looks like, it doesn't look exactly like I drew it, it just has to do with the font, but we have gamma radiation, we have a beta particle, all that information is in your data book. When a nucleus undergoes decay, it gets excited and then de-excited and gives off a gamma ray. So I'll show you with this next example what that means. So usually, so we'll take this example here with our thorium, when an atom undergoes decay, like so this is alpha decay, it gets excited. So this is it's called the daughter nucleus, which it turns into. It's in an excited state, and it has lots of energy still in it in that excited state. So what that will do is it'll undergo a gamma decay. But gamma doesn't have any charge and it doesn't have any mass, so it just turns into the same thing. So it just goes from an excited state to an unexcited state, and that's it. Okay. Gamma is super easy. So gamma radiation has a very high energy, and radiation that's ionizing and can damage DNA, right? That was at the top of our energy when we talked about this in our physics unit. So we can use a Geiger counter to detect radiation, and because each type of radiation is different, they all have different penetrating abilities. So alpha is a really big particle, so it can be stopped by a hand. It can be stopped by a sheet of paper. That's what could stop an alpha particle. Beta is a lot better of a penetrating ability, so it could go through your hand, but a little piece of aluminum would stop it. Okay. Gamma is it's not a particle, and it's light, so it can go through a lot of things. So gamma has a great penetrating ability. It can go through your hand, it could go through aluminum, and we need a few inches of lead to actually stop it. Okay, neutrons, which we didn't talk about, can go through a lot more because they don't have any charge as well. Okay, so I think that's where we're going to end it today. I won't post any homework with this because I'll do that with the next lesson. But yeah, so that is all for today. Welcome to part 2 of nuclear energy. So we're going to talk about nuclear fission. So radioactive decay is a natural process and will occur spontaneously. So nuclei can also be made to artificially decay. And the way that you can do that is shoot a neutron at it, and that process is called nuclear fission. So this is what nuclear fission looks like. So when you do nuclear fission, you need a really big atom. And the biggest naturally occurring atom is uranium, and uranium works really well. Uranium-235 works really well for this. So you take a neutron, you shoot it at uranium, and what that causes is it causes the atom to split. It splits into a smaller nucleus of barium-141 and krypton-92. And during this process, it also releases 3 neutrons. So those 3 neutrons are really important as part of the process of nuclear fission. Okay, so you take a neutron, you shoot it at uranium, it breaks into baryon and krypton, and then 3 neutrons. So nuclear fission breaks large atoms up into smaller ones, and in the process releases some energy. So during the process, 3 more neutrons are released, which are able to collide with more nuclei. And this can create a chain reaction which will explode uncontrollably. So this is what happens. So remember that we're just talking about one tiny nucleus. In a gram of uranium, there's trillions and trillions and trillions of these nuclei that can do this reaction. So we shoot 1 neutron at uranium, it splits it, fires off 3 more. Okay. Now those 3 neutrons collide with 3 more uranium atoms, it splits them, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So these 9 are going to hit 9 more uranium atoms. They're each going to release 3, so we're going to have 27. So this is a chain reaction. This is how you create a nuclear bomb. It causes all the fuel to explode instantly, and you get a lot of energy released at once. So when water changes to gas, what type of reaction is this? So you talked about this in Science 10. So this is called a phase change. And when water turns to gas, it's a type of phase change called evaporation. I spelled it wrong. That's okay. So when gasoline burns, what type of reaction is it? Well, it's a chemical reaction. So we have a new type of reaction that we're adding to this, which is a nuclear reaction. So E equals mc squared shows what happens instead of reacting chemically, we convert our mass into pure energy. So with E equals mc squared, E is that change in energy, m is our change in mass, and c is the speed of light. Okay, and that's a constant, and this is in our data booklet as well. So let's do an example. So what is the equivalent energy in a liter of gasoline if its mass is completely converted into pure energy by Einstein's E equals mc squared equation? Okay. How far could you drive on 1 liter of gasoline if all of its mass was converted into energy? So we're going to do this 2 ways. So we're going to do it the way that we know and the way that we've done before. And we can use Hess's law to talk about the burning of gasoline. So gasoline is octane, which is C8H18. I combine it with oxygen, and it makes CO2 and H2O. I'm a little bit off the screen, but let me fix that. There we go. And it's going to make H2O gas. So to balance this, we have 8 carbons, so we need 8 carbons. We have 18 hydrogens, so 9 times 2 is 18. And then we have 16 oxygens here, 9 oxygens here for a total of 25. So if I go 25 over 2, then it's balanced. Okay, so now we're ready to do it. So we're ready to do Hess's law, which is products minus reactants. So my products are 8 CO2, so negative 393.5 kilojoules, minus 9 times negative 241.8 kilojoules. And then I have to look up octane on here, and it tells me that octane is 1 times negative 250.1 kilojoules. So that's energy for octane. So let's calculate this. 8 times negative 393.5 plus, oops, this is minus, that should be plus. We add our products together. Plus 9 times negative 241.8. Close that double bracket, and then we're going to subtract it from 1 times negative 250.1. And we get the energy released from this reaction is negative 5074.1 kilojoules. So that's our energy released in our chemical reaction. Well, this is a chemical reaction. Let's do a nuclear reaction. So with nuclear reactions, we use E equals mc squared. And these ones, oops, my calculator's still in there. We use E equals mc squared. And what we're going to do is we're going to take the 0.954 kilograms of fuel, and we're going to convert it to pure energy by multiplying it by the speed of light, which is 3 times 10 to the 8 meters per second squared. So if I calculate the energy released from that reaction, so if I go 0.954 times 3 times 10 to the 8 squared, I get 8.586 times 10 to the 16, and this one's in joules. So if I switch this into kilojoules, it'd be times 10 to the 13 kilojoules. So you can see how much more energy is released in a nuclear reaction than this one. So this is 1 liter of gasoline. So if you think of this as 1 liter of gasoline, maybe you'd be able to go 10 kilometers on 1 liter of gasoline. So if we wanted to figure out how far we could go if we converted as mass and energy, well, if 5074.1 kilojoules can bring us 10 kilometers, well, how much could 8.586 times 10 to the 13 kilojoules bring us? And we can just cross multiply and divide. So cross multiply and divide, and we can figure that out. Oops, sorry, I set up my arrows the wrong way. We need actual numbers. So this is cross multiply, and this is divide. Okay. So we have this here, so I'm going to multiply it by 10, and then divide it by 5074.1. So I would be able to go this many kilometers, which is a lot of kilometers. So just to give you an idea, the sun is 150 million. 150 million, yeah, 150 million miles away. So you would be able to travel to the sun 1,128 times on 1 liter of gasoline. 1 liter of gasoline. This is how many times you'd be able to travel to the sun. So that's a lot. So what I'm trying to say here is that there is a ton of energy in nuclear power, way more energy than in chemical and phase change. Okay, so what you need to know is phase change is the lowest amount of energy, right? Think of how much energy it takes to turn water into a gas, right? You leave a glass of water on a table and just the energy in the air can make that happen. Chemical is medium because it's the middle one, because, you know, burning something gives off a lot of energy, but E equals mc squared and nuclear energy gives off way, way, way more energy than either of these two. Okay, so let's do an example. The production of free neutrons caused an uncontrollable release of energy, which led to the first atomic bomb. Use page 8 of your data booklet to determine the energy released from the reaction. So this is the reaction. This is a typo. This should be uranium-235. So just change that up. So this is our reaction. So I'm going to show you how to do this question. So I just need to open up the data book so we can take a look at it. So on page, what is it? There we go, page 8 of our data booklet. You have all this information right here. So this is the information that we want to use. So I'm going to write out the reaction that was given to us there, just so we have it handy. So we have 1 neutron and uranium-235. So I don't know why I'm writing these so high. Sorry. 1 neutron and uranium-235. And it turns into barium-141. And krypton-92, and 3 neutrons. So I can write it like that. I have 3 neutrons there. So what I need to do is, where the energy comes from for this reaction is, you can think of this as our reactants, and these are our products. Our reactants are always just a little bit heavier, and our products are always just a little bit lighter. So when we go from heavier to lighter, there's a difference in mass, and that difference in mass is converted into energy, and that's where the energy comes from, is that difference in mass. So we just need to find the mass of these, and we need to find the mass of these, and subtract them. That's all we do. And we can find the masses on our data booklet. So our first one is a neutron. So you'll find all neutron, protons, stuff up here. So here's a neutron right here, and it gives us the mass. Okay. So I have 1 of them, and it has a mass of 1.00866. And you have to be careful with these up here. It tells you that these are all in times 10 to the negative 3. So I need to add that times 10 to the negative 3 kilograms. And then my other one is uranium-235. So I find uranium, and they're all in alphabetical order here. Uranium, there it is. Uranium-235. And I'm just going to write that down. I have 1 of them, and it has a mass of 235.043. 92, and remember it's times 10 to the negative 3 kilograms. So I'm going to show you what my screen looks like. So I just wrote down the mass. I have 1 of them, and they're times 10 to the negative 3, 1 times 10 to the negative 3, like that. So what I'm going to do is I'm going to add these 2 numbers together in my calculator. So I'm going to go 1 times 1.00866 times 10 to the negative 3. And I'm going to add it to 1.235.04392 times 10 to the negative 3. Oops, I forgot my bracket around that. And it's 1 times, not 1 point. Okay, and I think that's all good. So that's going to be my total mass. So that's the mass of my reactant, which is 0.236 0.05258. Okay, so make sure you're trying this along in your calculator and make sure you get that answer. So now we need to do the same thing. So we need to add up these guys here. So we have barium, we have one barium-141, we have one krypton, and we have 3 neutrons. So I'm going to add those guys up. So I'm going to look on my data booklet. So barium is our first one, so we have to select barium. There's barium-141. So this is the mass of barium-141. So I'll go 1 times 140.91441 times 10 to the negative 3. And then I have to find krypton. There's krypton 92. So there's one of them. So 1 times 91.92611 times 10 to the negative 3. And then my last one, I have 3 neutrons. And remember that I find neutrons up top here. So 1.00866 times 10 to the negative 3 kilograms. So I can show you my screen where I wrote that all down. So I'm going to add those together on my calculator. So I'm going to go 1 times 140.91441 times 10 to the negative 3, close my bracket, add it to 1 times 91.92611 times 10 to the negative 3, close my bracket, add it to, so I have 3 neutrons, right? There's 3 neutrons on that equation that I make. So 3 times 1.00866 times 10 to the negative 3, close my bracket, and that's the mass of my products. So you can see there's a little bit of a mass difference, and my reactants are heavier than my products. So if I take this and I subtract it from this, this is the mass difference, and that's what I want. That's the most important value. That's what I was looking for, was my difference in mass. So my difference in mass between these two is 1.8608 times 10 to the negative 4 kilograms. So from there, once I have that change in mass, then it's really easy. Then I just have to use E equals mc squared. So I take my 1.8608 times 10 to the negative 4 kilograms, and I just multiply it by the speed of light squared. And I can find out my energy released in this reaction. So I'm going to take my answer, I'm going to multiply it by the speed of light squared, and this is how much energy was released in the reaction. So I would go 1.67 times 10 to the 13 joules of energy is released in the reaction. Okay, that's it. So let's try a board question. So pause the video, do this, and see if you can get the right answer. So I'm going to make this smaller so we can see both. Oops. Yeah, that's good. And yeah. So my reaction is okay, so these are my reactants. So I just have to take the mass of my reactants. So you have to select the right one. So this is polonium-210. And there might be, see there's more poloniums in there, but we want polonium-210. So we'd write down the mass number. I have one of them. So I have 1 times 209.91441 0.98286, and remember to put that times 10 to the negative 3 kilograms. So that's all I have as my reactant. My products over here is I have lead 206, so I have one of them. And there's going to be more than one lead, so we have to select the right one. So this is lead 206 right here. It's got to be exactly the same. So 1 times 205.9745 times 10 to the negative 3. And I add it to my other product. So you should recognize this is an alpha particle. So you would find alpha particles up top here. So this is where you'd find it. So it's got a mass of 4.00151 times 10 to the negative 3 kilograms. Okay, so I'm going to add, well, this is just whatever that number is, and then I'm going to do this. So this is in my calculator. So yeah, if I just go 1 times 209.98286 times 10 to the negative 3, obviously I'll just get that. And then 1 times 205.9745 times 10 to the negative 3. I'm going to add that to, oops, close my bracket, add that to 1 times 4.00151 times 10 to the negative 3. And that's the mass of my products, right? So there's a little bit of a mass difference, so I just take my reactants and I subtract it from my products, and I find that mass difference, right? And then from there, once we find that change in mass, we can just use E equals mc squared. So we take this value and we multiply it by the speed of light squared, and that's how much energy is given off in your reaction. So hopefully you got that answer, and if you didn't, try again and take a look at my numbers that I plugged in there and see if any mistakes were made. Hopefully I didn't make a mistake in there. Okay, so the CANDU reactor. So in a CANDU reactor, which stands for Canadian Deuterium Uranium Reactor, that's the main type of nuclear reactor used around the world. CANDU reactors run on uranium fuel rods, and I'll show you, I have a uranium fuel rod here that you can take a look at. Here it is. So uranium has a really, really high energy density, which means you store a lot of energy in a tiny little place. So this is what a uranium fuel rod looks like. They're that big, and in this tiny little fuel rod, it's equal to 807 kilograms of coal. So think of like an elephant worth of coal. 677 liters of oil, so a swimming pool of oil, or like my whole classroom filled with natural gas. All that energy is stored in that tiny little uranium rod, which is really good. Okay, so what they do is they take these uranium fuel rods, and they're not green, they're not glowing, they're not throbbing. All that they do is they heat up. So they heat up, and they heat up this water here. And after that, it's exactly the same as a coal reactor, right? So what we have, if we wrote out our energy conversion, so we start off with nuclear energy. Okay, nuclear potential energy. So we start off with nuclear potential in the energy in these fuel rods, and then it heats water, so it turns into heat. And then this heat is shot through these pipes. So we have kinetic energy of our water, which turns these turbines and turns it into electrical energy, right? Which is exactly the same as coal, only the starting energy is different. So you need to be able to control this reaction because this would just heat up and basically turn into a nuclear bomb if you let it heat up. So what it has is it has these things called cadmium rods, and they absorb some of the neutrons. So it says that it makes 3, but we don't want to make 3 because that's kind of how you make a nuclear bomb. So the cadmium rods will absorb 2 of the 3, so it slows that reaction, and you're able to control it and add more energy, so more neutrons, less energies, less neutrons, depending on the needs of your city. Okay, so remember that this is a fossil fuel plant, and we start off here. We've got chemical potential in the coal, and then we've got heat, and then that heat turns into water, heats the water, and that water turns into kinetic energy, and then everything turns each other, and then we get electrical energy. So it's exactly the same, except for that chemical potential energy to start. Okay, so similarities and differences between nuclear fuel and fossil fuel. Similarities is they're both non-renewable. So they're both non-renewable. Similarities is all same energy conversions. I'm gonna write this on the board here. So all same energy conversions. And they both create thermal pollution. And remember that thermal pollution is hot water. So if you send hot water back into a lake or a river, it lowers the amount of oxygen in that water, and it can choke out the fish in that water or plants living in that water. Okay, so that's the similarities. Differences is coal makes SO2, CO2, particulate matter, and nuclear doesn't. Nuclear is a very clean type of energy. It doesn't cause any emissions into the air. Nuclear creates waste that you have to store. So after those fuel rods have been used for a while, they don't work as well anymore, and then you get rid of them. So you can't just like throw them out in the garbage because they are radioactive. They do release alpha particles, beta particles, all of that. So you just have to store them, and we really have no way of getting rid of that. So yes, but you don't want a whole bunch of nuclear waste storage facilities. You have to line them properly with lead to make sure that they don't give off any radiation. So that's the bad part about nuclear fuel. Okay, and then the last thing that we're going to talk about today is fusion reactions. So fusion reactions are the reactions that happen on the sun, but we can also make them happen on the Earth. So what you really need to know is that fusion is when you take hydrogen and you turn it into helium, and it gives off a whole bunch of energy. That's it. So hydrogen to helium. So just to show you how much energy it gives off. So this is a picture here, and this is one of the largest reactions. So this is TNT, dynamite. So this is how big an explosion can be, 1 kiloton. And then this explosion was the bombs dropped on Hiroshima and Nagasaki in World War II. And this is how big the explosion is, so quite a bit bigger than any chemical reaction, right? This is a chemical reaction, and this is a nuclear reaction. But this is fission reaction, where you take uranium and you split it up, or plutonium and split it up. This here, this is all drawn to scale, is a fission reaction. So this is Castle Bravo, which was a nuclear hydrogen bomb that was dropped, and it's much, much, much bigger. So this is Fat Man. This is the bomb that was dropped on Hiroshima and Nagasaki, one of the two. But yeah, so that's what it looked like. So this is Castle Bravo. So this is a little video here that shows the explosion. This is actual footage of it, and it ended up being way bigger than they thought it was going to be. And yeah, it was not very ethical. They did it on the Bikini Islands, and it killed a lot of the indigenous people there, which isn't good.
Bravo was a hydrogen bomb. using solid thermonuclear fuel, confirming the designs of Edward Teller and Stan Ulam, and paving the way to producing aircraft-deliverable hydrogen bombs and more effective weapons. Significantly exceeding its expected yield by 2.5 times, Castle Bravo, with an explosive power of 15 megatons, stripped islands clean of vegetation and took the scientists by surprise. The huge explosion released large quantities of radioactive debris into the atmosphere. This resulted in the exposure and contamination of some servicemen, natives, and the crew of a Japanese fishing boat, which had gone unnoticed in the security zone around the blast. This incident pushed the dangers of fallout from nuclear weapons clearly into the public mind.
So Castle Bravo was a hydrogen or thermonuclear or fission bomb that was detonated in 1954 in the Bikini Islands. In a hydrogen or thermonuclear bomb, you're recreating the reaction that happens in the sun. So you're turning hydrogen into helium. So this reaction is hard to do because in order to make a fusion reaction happen, you need really high temperature. So what they do is they place a fission bomb, so uranium bomb, inside of the hydrogen fusion bomb, and they explode this one first, and then that creates the large temperatures needed for your hydrogen bomb to explode. So it's a bomb within a bomb. It's like a turducken of bombs. So the energy released in a thermonuclear fusion bomb can be more than 10 times greater than a fission bomb. So way, way, way more energy in a fusion bomb. So this is bombs, this is bad things with it, but you could also power cities with it. So we have lots of hydrogen here on Earth because water is made of 2 parts hydrogen, so we could get it. So if you are just turning hydrogen to helium, then couldn't you just use that to power cities, and we have an unlimited energy source? So why don't we use it? Well, it's not just that simple of turning hydrogen to helium. And the main problem that is bad is the hot temps. So to make fusion happen, you need to be more than 1,000,000 degrees. And if you have a reaction happening at 1,000,000 degrees, there's no container that can hold that. It would melt it would destroy everything, and it would blow up. So that's the biggest problem. So they're doing research on using magnetic fields to contain the hydrogen, because magnetic fields wouldn't be affected by the temperature. So they're in 10, 20 years from now, yes, they will have fusion reactors, but they just don't have them yet. And the other great part about fusion is that you make helium, so it's a lot safer than the nuclear waste products of fission. Okay, that is it. I'll post an assignment, and if you have any questions, let me know.